Hello and welcome everyone to today's live session on NPTEL course of Foundations of Cryptography. So let me share my screen first. So first I will just discuss the week 6 assignments posted on NPTEL website, and then I will proceed to this week's content. Okay. So the first question was select the incorrect options from the Markle-Damgard transformation. It employs a single stage approach for the transformation. So as you know, as part of the Damgard Markle-Damgard transformation, there is this multiple stage of fixed length compression function, and after applying that multi-stage of application of fixed length compression function, we get hash function for variable length inputs, right? So this statement is definitely wrong. Next option given is this construction will always add a padding to the message which depends upon the length of the message. That is true according to the construction of Markle-Damgard paradigm. So there is always one last block which contains information about the length of the message. Okay. The initial vector IV used in this construction has to be fixed. This is again true statement. And collision resistance of the transformation is independent of the collision resistance of the compression function used in its construction. This is wrong because if you remember that when we try to prove the collision resistance of Markle-Damgard construction for variable length input, for hashing variable length of input, then what we do is that we basically try to see from right to left and analyze that what happens. Like first we assume that there is existing collision for Markle-Damgard construction for two different input, let's say some x and x dash, and then we see that at each step of the at each stage when there is this fixed length compression function box is there. So then what happens is that at every stage, whenever we assume that at some particular stage the collision happened, that is for particular value of input from previous stage, and the that ith specific message block for that particular input, the output are same, then it boils down to the problem that there is a collision of the underlying compression function, fixed length compression function, right? So if hence we conclude that because we already know that the underlying fixed length compression function is collision resistant except with negligible probability, then we conclude that hence our Markle-Damgard construction, which uses multiple stage of applying fixed length compression function to variable length input, then that construction is also collision resistant. So of course there is dependency between the Markle-Damgard construction and the underlying fixed length compression functions collision resistance property. Okay. So only true options here are the second and third one. Okay. Next question is choose the incorrect options from the following. Hash functions can either be used for compression or for expansion, but not both. Okay, the only target of hash function is that if you remember, we denote hash function as 0,1 to the power star that maps to some 0,1 to the power L specific, right? So the input can be anything. It can be it can be of lesser length than the output, and it can be of higher length than the output space, right? So if your output is L bit long for your hash function, then the input length can be less than L also or more than L also. Okay, that is not a problem. So if it is less than L, then the hash function is an expansion function, or if it is greater than L, then it acts as a compression function. But does not matter. The main target of hash function is to map the whole range of the whole domain or whole all possible inputs to some particular codomain of some specific bit length, right? Of course, collision resistance is the necessary property for cryptographic hash function. But main thing is that it can be used for both compression and expansion. No restrictions on that. So first statement is wrong. Second statement says that the probability of finding a collision for a given hash function depends on the codomain of the function. Okay, this is correct, because if you see, whenever there is attack on some existing hash function, it basically tries to exploit the fact that how small is the codomain of that hash function. So the trivial attack on to find a collision. So basically, attack on a hash function means that you are successfully coming up with two such different messages, distinct messages, x and x dash, such that x is not equal to x dash, such that h of x is equal to h of x dash. If an adversary is able to come up with such pair, we say that it has been able to find a collision, and hence the collision resistance property of the hash function is not there anymore, right? Now, if is, let's say, the codomain of your hash function or range of your hash function has size some capital N, right? Then what happens is that if you query for n plus one distinct input from the input space of the hash function, then you will be certainly get two such distinct input among those n plus one input query, which will map to same output in the hash function, because the hash function output space has size n. So by the application of pigeonhole principle, you can see that because as there are only n number of outputs available for that hash function, and you are querying with n plus one different number of inputs, there has to be at least two such input query which maps to same output by the hash function, right? So that's why we always require that the codomain of the hash function should be large enough, so that this n plus one number of doing n plus one number of input query to the hash function does not leak collision. So this must be computationally infeasible to perform n plus one number of query. Okay, so n should be large enough. So yes, the probability of finding a collision for a given hash function depends on the codomain of the function. Third option says that we can construct a hash function with zero probability of collision. This is never true. Why? Because the input space is greater than the output space, because as I just mentioned, that hash function is denoted as 0 1 to the power star to some 0 1 to the power L, right? So you have your limited size of output space, and your input can be anything, and no doubt your input space is quite larger than your output space, and so there must be, like, it has to be some many to one function, right? So there must be collision, but only required property of the hash function is that it should not be easy to find such two inputs which maps to the same output. That's what the collision resistant property of hash function says. So for an adversary to find a collision, the probability of finding a collision should be negligible. It should not, like, it cannot be zero. It is enough to be negligible. Okay. So constructing hash function with zero probability of collision is practically not possible. And hash algorithms can be used in MAC as well as in the generation of PRGs. That is the fourth statement given. So as you may have already seen in the lectures that yes, hash algorithm can be used in Mac as well as in generation of PRG, right? So if you are already uh, acquainted with the HMAC thing where hash functions are used to construct MAC, and also in generation of PRGs also, because if you consider hash function as a random oracle, so hash function modeled as random oracle, in that scenario basically the adversary does not know the inner construction of the hash function, and it can just send some query input x, and the um, oracle gives it back h of x, and uh, if x is not seen beforehand, like in some other query, you have not seen hx for that particular x beforehand, then for a new x, the output hx should be uniformly random on the output space, and should be independent of previous outputs. Okay, so that is the property of like random function, or you can say that with that, using that property, you can uh, think of uh, using hash function in generation of PRG. Okay, so for this question, our correct option was only the second and fourth option, right? Proceeding to the next question. Uh, Given H and G are collision resistant hash functions, which of the following is or are collision resistant? Uh, so you are given the first construction as f1x equal to hx concatenated with gx. So let's assume that f1x is not collision resistant. What would that imply? That is, it is easy to find such pair of inputs x1 and x2 such that such that f1 of x1 is equal to f1 of x2, right? That is the property of collision resistance. So if it is not collision resistant, you can easily find such pair of input x1, x2. Now f1 of x1 equal to f1 of x2 implies h of x1 concatenated with g of x1 is equal to h of x2 concatenated with g of x2. I am just expanding the expression of f1 x, right? Now compare the both side of the equation, that is h of x1 concatenated with g of x1 and h of x2 concatenated with g of x2. If these two strings are completely equal to each other, that means that first half of the string is also first half of the left hand side string is also equal to the first half of the right hand side string, right? Which means nothing but h of x1 is equal to h of x2, and similarly g of x1 is equal to g of x2, right? If that happens, it means that using the collision finder of f1x, you can easily find collision for the hash functions g and h both, right? But you already know that g and h are collision resistant hash function, so that must not be easy. And by contradiction, we can say that finding collision in f1x is also hard. And that's why we conclude f1x is not, f1x is a collision resistant hash function. For the second option, f2x is equal to h of x concatenated with 1. Here also, if you see, the only difference between hx and f2x is that one extra 1 at the end of the hashed string, right? So similarly, you just analogous to the first construction of f1x, here also we can argue that if some adversary is able to find such collision pair x1 x2 for the hash function f2, that would imply that f2 of x1 is equal to f2 of x2, which implies that h of x1 concatenated with 1 is equal to h of x2 concatenated with 1. And if you just ignore the last bit 1, for both the left hand and right hand side strings, then what you are left with is h of x1 is equal to h of x2. And so we are able to find the collision in the hash function h, which is not true again because h is already known to be collision resistant. And hence we conclude that F2 is also collision resistant. Otherwise, we would have been able to use that to find collision in H. Okay. So first two options are proved to be collision resistant. Coming to the third option, F3x is equal to H of x XORed with G of x. Here, let's see that H and G are given to be collision resistant hash functions, but there may be the obvious case that H is equal to G, right? Because it's not given in the question that they are distinct collision resistant hash function. So just to see the most obvious possibility that you can be given G and H as the same hash function, and if that is the case, for sure F3x will be H of x XORed with H of x, and that would be all string of all zeros, and irrespective of whatever input x is given to F3, it always will be output all zero string, right? And that is certainly not collision resistant. So we finding this particular counter example, we will conclude that F3 is not collision resistant. And by intuition, you can see even if G and H are distinct hash function, then also it can be the case that there is some input x for which H of x, there can be in fact multiple such instances of x for which H of x and G of x value could be same, because at least collision resistance property of individually H and G, these two hash functions, does not anyway ensure collision resistance of F3, right? Just like the previous example, here you cannot say that H of x1 XORed with G of x1 equal to H of x2 XORed with G of x2 will somehow be against the collision resistance property of individually H and G. So that is not the case. So by intuition also you can see that even if G and H are not distinct, then also even if G and H are distinct, then also F3x may not be collision resistant. We can't say for sure, right? So only two options here, only collision resistance hash function construction is F1 and F2 in this question. So proceeding to the next question, which of the following statements is or are correct? First option given, information theoretic maps are secure only against an adversary running for polynomial time. We last week also we discussed in the live session in quite detail that information theoretic map are secure against unbounded against adversary with unbounded computational power. Okay. So, so this statement is, of course, wrong, right? Information theoretic maps are secure against even adversary with unbounded computational power. Perfect unforgeability is not analogous to perfect secrecy. That is the second statement given, which is true. Why? Because last week we discussed in detail that perfect secrecy means we are allowing the adversary to have unbounded computational power, as well as we are saying that in spite of allowing the adversary to have unbounded computational power, in case of perfect secrecy, your distinguishing probability between encryption of M0 and M1 is exactly 0. Okay, but in case of perfect unforgeability, which is the case of, say, information theoretic MAC, you are actually allowing the adversary to have unbounded computational power, but the adversary can come up with valid message tag pair with some negligible probability. It is not exactly 0. Okay. So that is the difference between these two cases. So it's not, they are not analogous. Perfect unforgeability is not analogous to perfect secrecy. This is true. Next statement is given: one-time IT secure MAC is not analogous to one-time pad used in encryption. Using the same logic as in the second statement, here also you can easily understand that one-time IT secure MAC, which is an information theoretic MAC, secure against unbounded adversary, but adversary is able to come up with valid message pair with negligible probability, where in case of one-time pad, the adversary, even if having unbounded computational power, it can gain any information about the underlying plain text by seeing the cipher text. That probability is 0. Okay, exactly 0. Now coming to the fourth statement, in the ideal cipher model, only the adversary does not have access to the working of the SPRP used in a given construction. Okay, so in the ideal cipher model, what happens is that any block cipher, so here as it is given some strong pseudo-random permutation viewed as a block cipher. So such block cipher, the internal details of the construction are not given to the any entity taking part in the particular cryptographic primitive. So constant any cryptographic primitive in ideal cipher model, then not only the adversary, rather all the entities taking part in that primitive, they all consider the block cipher to be some oracle, right? So internal details of how the block cipher works is hidden from them, and they consider the block cipher as some randomly generating output. So it just queries the oracle with x and k, and it get backs fk of x, where f is our strong pseudo-random permutation, right? So it is not only the case for adversary, rather all the entities taking part in the crypto primitive in ideal cipher model. So last statement, only the adversary, this thing is wrong. Okay, so the correct statements are second and third one. Proceeding to the next question. Let f 0 1 to the power n cross 0 1 to the power n mapping to 0 1 to the power n. So both key space and input space are n-bit binary string, and output is n-bit binary string. This is a keyed function, and h which maps the input space m to n-bit binary string. This is another function defined, and m is any binary string having upper bound of length as L. So L is the upper bound of the length of binary strings present in the space M. Now, also L is some polynomial function of security parameter. Then consider the keyed function f dash 0 1 to the power n cross m mapping to 0 1 to the power n, where f dash k m is defined as fk of h of m. Which of the following is or are true? So I guess this question was also discussed in the last session, but just for the sake of completeness, I will reiterate that here the way f dash k is defined. So if we want f dash k to be a secure PRF, what we require is that even after seeing polynomial number of functional output for inputs of adversary's choice, even after seeing those polynomial number of input and functional output pair, the adversary is unable to distinguish that whether it is interacting with a PRF producer or truly random function, right? So whether it is seeing or whether it is in the polynomial number of outputs that it sees against the query it raises to the challenger. So those outputs can be generated either using the PRF or using truly random function. Now, even after seeing such polynomial number of outputs, it cannot distinguish whether it is interacting with a PRF or a TRF, pseudo random function or truly random function. Okay, this is the required property for f dash k to be secure PRF. Now see its construction defined as fk of h of m. Now, if we see that f is secure PRF, but the inner function H is not a collision resistant function. Okay. Then what could happen is that there can be some message M1 and M2 such that H of M1 is equal to H of M2. Okay, because the hash function is not collision resistant, so adversary is able to come up with such pair M1 M2 such that H of M1 is equal to H of M2. And then what the adversary can check is that it can query the challenger with message pair M1 and M2 and see whether it is getting the same output from the challenger. If it is getting the same output from the challenger, it will conclude that, okay, I am interacting with a PRF. Otherwise, it will conclude that it is interacting with a truly random function. Okay. Why? Because H of M1 is equal to H of M2. So Fk of H of M1 will be equal to Fk of H of M2 in case the adversary is interacting with a pseudo-random function, like with this F dash K. So with non-negligible probability, the adversary is able to distinguish the output of F dash K of M from the output of some truly random function. Because in case of truly random function, irrespective, like in case of truly random function, with input M1 and M2, the output will be completely independent and uniformly randomly distributed over the output space. So there is very negligible probability of getting same output by querying with different input M1 and M2. But in case of F dash K, they will be essentially same because the hash function the function H is not collision resistant for M1 and M2. Okay. So in order to F dash K to be collision resistant, our required property is that H has to be collision resistant. Also, F also needs to be secure PRF itself. Otherwise, there is no meaning of constructing F dash K, right? So if F itself is not secure, then F dash K is obviously not secure. Okay. So the last option is the only correct one, that F is a secure PRF and H is collision resistant, then only F dash is a secure PRF. So that is the week 6 assignment discussion completed. Now we will get into this week's topics, which are attraction hash function, then random oracle, and then authenticated encryption. Okay. Now, first problem, which of the statements is or are true? So I hope that you have already gone, like you have already watched the lectures posted on YouTube by the professor. So this is the basically week 7 content, and your submission deadline for this week's assignment is probably around 15th or 16th March, I guess. So discussing similar problems on these topics may help you in solving those assignments. Okay. Now, so coming back to the first problem, which of the statements is or are true? First option given as birthday attack on cryptographic hash function requires at least q equal to root to n number of distinct queries to ensure collision with probability at least q into q minus 1 by 4n. Okay. Here n is the size of codomain of the hash function. Okay, like if you would like to answer, then you can unmute yourself and answer, or you can type to chat, whichever is okay with you. So let's proceed with the given statements one after another. So the first option is it correct or not? That birthday attack on cryptographic hash function requires at least root to n number of distinct queries to ensure collision with probability at least q into q minus 1 by 4n. You can write to chat. Okay. So this is true. it has been already proved in the lecture that how this lemma come into place, that with uh, 3, which of the statements are true? Okay, what do you mean by 3? The third option is true. Yes, the third option is true. Thank you. Just now I discussed probably, right? Yes, third option is true. Apart from that, let's say first option, if we look at first option is true. If you watch the lecture on the YouTube, okay, uh, 2, right, 2 is also, you are correct, all. Yes, thank you. So all of them is the correct option actually, right? So we should keep the codomain of hash function large enough in order to prevent birthday attack. That is true. And the reason being the third statement actually, that q equal to n plus 1 number of distinct queries to hash function finds collision with probability 1 due to Pigeonhole principle. So in order to prevent this kind of trivial attack, we should keep the codomain of hash function large enough. And birthday attack, this is a well-known theory proven in the lecture also, that with this many number, from here only why the name birthday attack came. So from here only, that if you just replace the number n with 365, which is the number of possible dates for any person, avoiding the leap year scenario. So there are 365 days in the year, and that any person can have birthday on any of those days, 365 days. So you just replace 365, replace n with 365, and you will get q equal to 27. So you, if you have a gathering of 27%, then you will have probability of collision in their birthday. So 2% having same birthday, that scenario can occur with probability almost half. Okay, if you replace this expression q into q minus 1 by 4n, replacing q with 27 and n with 365, you will get that probability is almost nearby half. So that is very interesting. That's why the name birthday attack comes to place. Okay, proceeding to second problem. Which of the following statements is or are correct? Merkle tree is full binary tree with hash pointer. Tampering with any data node of the Merkle tree is infeasible due to collision resistance of the underlying hash function. Proof of membership of any data node in Merkle tree needs exponential storage, and all of the above. Well, okay, thank you. So yes, so if you want to answer this question, which one among them are correct? Merkle tree is an application of hash cryptographic hash function. Would like to answer which one you think is or are true? First statement, Merkle tree is full binary tree with hash pointer. This is true actually. So you know the construction of full binary tree, right? So all the nodes except the leaf nodes will have its both left and right child, right? That is the construction of full binary tree. And if you just usually what happens is that in a binary tree, if you see, the each node of the tree will have pointer to its left child and right child, right? So if you just replace those pointers with hash pointer, then what you get is like Merkle tree construction, and the hash pointer is nothing but a pointer. Essentially it will store the memory address for the left and right child. Along with that, it also keeps hash of the all the nodes below that node, right? So this hash information of all the node below it will be stored in the um, hash pointer of each node, right? So basically, if you look at the root node will contain the summary of information present in all the data nodes of the tree. So some hash value of all the information contained in the tree is summarized as some hash in the root node. So and the main uh, motivation to do that is avoiding any tampering with the data. So if you look at the second option, it says that tampering with any data node of the Merkle tree is infeasible due to collision resistance of the underlying hash function. So what happens basically is that whenever you change any data node of the Merkle tree, then the parent node of that changed data node, in order to maintain the consistency of the hash value, you need to change the parent node of that corrupted data node as well with the hash value of corrupted data, right? And like that, if you move further from bottom to top, okay, you will gradually reach the root node, because there is always path to all the data node of the tree from the root node. So any path starting from any corrupted data node will gradually reach to the root node, and thus the root node hash value also needs to be changed whenever there is change in any data node's information. Okay, whenever there is change or corruption in any data node, that will affect the hash value stored in the root node of the tree. And there is very negligible probability that your original information and the corrupted information will hash to the same value because of the collision resistance property of the underlying hash function. And so that's how it actually avoids any type of temperament with the data. So tampering with any data will be detected by using the Merkle tree. Third option, proof of membership of any data node in Merkle tree needs exponential storage. This statement is wrong actually, because proof of membership means that say any user of that Merkle tree information, so the user essentially always store the root node or the hash information stored in the root node with it, but it does not store all the nodes of the whole Merkle tree with it always, in order to efficiently use its space, right? But whenever it needs some particular data, let's say ith leaf node is the data that it requires, so it queries for that data and it gets back that particular data node. Now it has to somehow verify that whether it is getting the correct value stored in the ith node or not. And for that, if you think that you need to calculate the whole hash value of the whole tree, and for that you need all the data nodes and intermediate nodes of the Merkle tree, that is not true. You just need the nodes present in the path from root to that particular data node that you have queried for. And only with those, say if the height of the tree is h, then you need only order of each number of nodes present in the path between root to that particular data node, and by calculating the hash of those in that path, you can check that whether your stored hash value of the root pointer is equal to the hash value you are getting using computation upon those nodes present in that particular path. So you just need to store only linear or like linear in height of the tree, that number of nodes. So you don't need exponential storage for getting proof of membership, whether that particular data node is actually member of Merkle tree or not. That is the proof of membership thing. So you just need linear storage. Okay. Okay. So next question. Okay, the only correct option here was Merkle tree is full binary tree with hash pointer, and tampering with any data of the market is invisible due to okay, the last option I forgot to uh, discuss. So last statement is given as small space birthday attack is derived to reduce time complexity of original birthday attack. Will you like to comment on this statement, whether it is true or false? Small space birthday attack is derived to reduce time complexity of original birthday attack. What original birthday attack does is that it actually does some q number of queries to the hash function, q number of distinct input queries. I don't know how to explain it, whether it is true or false. Not the explanation. If you write true or false. Okay. False, I guess. Okay. This is false. True statement is actually small space birthday attack is derived to reduce space complexity of original birthday attack. Okay, not the time complexity. If you see the name only, small space birthday attack. So this small space is to reduce space complexity of original birthday attack. What happens in original birthday attack? If you remember that you raise q number of queries, okay, to the hash function, q number of distinct queries, say x1 x2 to xq, and you store the corresponding hash value h of x1 h of x2 to h of xq. All this q number of values you store, and you try to find some collision of this hash value. So there, if there is some xi and xj such that h of xi is equal to h of xj, that's what you try to find, right? Now, for that you need order of q storage, right? But in case of small space birthday attack, we exploit some particular property which says that if there, let's say you have q number of queries, right? So you have some say capital I and capital J indexes between 1 and q. So 1 is less equal to capital I, less equal to capital J, less equal to Q. Okay. So I and J, capital I and capital J are between 1 and Q. So such I and J exist so that H of, okay, let me just repeat one thing, that you are actually computing hashes of a sequence of values. So you start with some x1, okay, you compute h of x1, let's denote it as x2. So x2 is nothing but h of x1, and then you go on computing hash of the previous output. Okay, so you get x1, then you get x2 equal to h of x1, then you get x3 equal to h of x2, then x4 equal to h of x3. So h of xi, so basically xi is equal to h of xi minus 1. Okay, so you have this q number of sequence of hash values, okay, such that h of xi is such that in this sequence, say x1 x2 to xq, in this sequence each xi is equal to h of xi minus 1. If you have such sequence, and if you have capital I and capital J between I and Q in such a way that x of I is equal to x of j, then the theory says that you will get some I greater than your capital I, small I greater than capital I, such that hash value such that x of I will be equal to x of 2i. Okay, am I clear? So if you have such a sequence and you have such I and j, capital I and capital J, then you will find some small I greater than capital I such that x of I is equal to x of 2i in that sequence. And from that, by backtracking, you can find the exact collision in that sequence. Okay, so you basically, for each query, you have to store the value of xi and x2i. That requires constant amount of space. You don't need to store all the q number of hash values with you to perform the attack. So that requires only constant storage space, and small space birthday attack is derived to reduce space complexity of original birthday attack. Okay. Hope I am clear. And I'm proceeding to the next question. So which of the following is or are true for the hash function based commitment scheme? Collision resistance property for the underlying hash function is not necessary for the binding property of the commitment scheme. Collision resistance property for the underlying hash function is necessary for the binding property of the commitment scheme. And the binding property can be proved only in the random oracle model. If you would like to answer. First two statements are, I think, just opposite of each other. 2. Collision resistance property for underlying function is necessary for, yes, you are correct. It is true. And first one is of course then false. And binding property can be proved only in the random oracle model. This is also false. Okay. Why? Because the binding property can be proved just using the collision resistance property of the underlying hash function. So if you just for the sake of completeness, I will briefly discuss. So commitment scheme is an application of hash function. Commitment scheme can be built using hash function as the underlying primitive. And then commitment scheme has two necessary property, hiding and binding, right? So in case of hiding, you ensure that seeing the commitment C corresponding to some message M, the receiver of the commitment cannot guess the value of M, right? That is the hiding property. The value of M is hidden from the receiver unless it receives some opening information from the center. Okay. And the binding property ensures that whenever there is some commitment C generated from message M using some randomness R, then there should not be another pair of M dash and R dash, M dash some another message and R dash some another randomness, such that M dash and R dash by the commitment algorithm maps to the same commitment C. So this is just similar as the collision resistance property of the hash function. So by applying the collision resistance property of the hash function, we can ensure binding property of a commitment scheme. But and then for ensuring hiding property of the commitment scheme, we actually need random oracle model, because the collision resistance property of hash function is not sufficient enough to argue the hiding property of a commitment scheme. So we need to see hash function as modeled as random oracle. Okay. And that's when we can actually prove the security of the hiding property of commitment scheme. Okay. So the last statement is wrong, because binding property can be proved only by the collision resistant property of the hash function. No need to go to the random oracle model. That is needed for hiding property. Okay. So proceeding to the next question. Which of the following is or are true about the random oracle model? First option, cryptographic primitives built upon hash function are proved secure under ROM, that is random oracle model, when collision resistance property of hash function is enough to ensure security of the primitives. Hash functions are considered to generate random output in random oracle model. No entity in the crypto system should have knowledge about the internal working of a hash function when modeled as random oracle, and all of the above. You can, I think these are very easy to answer. Also, if this meeting ends, you join in the same link. Okay. 2, 3. Okay. So hash functions are considered to generate random output in ROM. That is true, right? Thank you. And no entity in the crypto system should have knowledge about internal, right? This is also true. And the first option is of course wrong, because we already know that when collision resistance property of the hash function is not enough to ensure security of the primitives, then only we go for modeling hash function as random oracle. Okay, so first option is wrong. So 2 and 3 are the correct option, correctly answered. Thank you. Proceeding to the next problem then. To choose the incorrect options, programmability of random oracle allows the attacker to set the answers to the random oracle queries raised by another existing attacker who is being used by the first one in a reduction based proof. Extractability of random oracle allows an attacker to be aware of the random oracle queries made by another existing attacker who is used by the first attacker in a reduction based proof. Each entity in a cryptographic primitive is allowed to access the random oracle and they can see each other's query. That is, on which input they query the random oracle, and all of the above. You would like to answer? Not 3. You are saying 3 is not correct. They cannot see each other's query, basically. Right, you are correct. So first two options are correct. Yes, you are right, actually. Okay. So that is the definition of programmability of random oracle and extractability of random oracle. I will just briefly repeat these things, that these are two important properties of random oracle. What happens is that whenever you do some reduction based proof, in reduction based proof, what happens is that you the scheme that you want to prove to be secure, then what you do usually is that you first assume that that scheme is not secure, and you design some game between attacker and challenger, and then use that attacker who is actually, you assume that he is able to attack your crypto system. Then you can use that attacker to attack some other crypto system on whose security your first system is built on. So basically, using that attacker, you are able, you show an attack to the hard primitive, and then by contradiction, you conclude that if there is an attacker which can, I should actually be clear. Okay, let me say that pi is some primitive that you are trying to prove to be secure, and its security is based on some another primitive, say pi dash. Okay, you want to prove that pi is secure and pi's security is based on some other scheme pi dash. Then what you do is that you assume that pi is not secure first. Then if pi is not secure, there must be an adversary A which is able to launch successful attack on the scheme pi. Then using that attacker A, you design another attacker A dash who is able to launch an attack on the existing scheme pi dash, which is already known to be secure. And because using A dash is able to launch an attack on using A dash is able to launch an attack on pi dash, which is known to be secure, then there is a contradiction. So we conclude that such adversary A for scheme pi cannot exist, who is able to successfully launch an attack on pi. So we conclude that pi is secure. Now, in such a reduction-based proof, let's say our adversary A needs some random oracle access. Now, the attacker A dash is using A, right? Now, if A is doing some query to random oracle, by the extractability property of random oracle, A is actually able to see for which inputs A is querying the random oracle. So A dash is able to see the query inputs to random oracle raised by A. That is the property of extractability of random oracle, and programmability says that A has the power to set the random oracle value of those query inputs, because as this is a just reduction based proof, there is no such real scheme running in practice and there is no instantiation of hash function or instantiation of random oracle. Then basically in the proof, the attacker A dash itself assigns some value to the query input of A, and that's how the random oracle table is filled up, and that is the property of programmability of random oracle. Okay, and the third option, each entity's cryptographic primitive is allowed to access the random oracle and they can see each other's query. That is basically any entity in cryptographic primitive is allowed to access the random oracle. That part is true, but they cannot see each other's query actually. Okay, all the queries to random oracle are private. Sure, if you are always free to leave. If you have any work, you can leave. Okay, thank you for joining. Okay. So let me proceed to the next question. Select the incorrect statements. Output of a PRG is pseudo-random on uniformly random seed. Seed of a PRG is known to adversary. Adversary can query random oracle with any input of its choice. The output of random oracle on some query input appears to be independent and uniformly random over the range if query is made by an entity for the first time. Okay. So I will just maybe discuss the options. So output of a PRG is pseudo-random on uniformly random seed. This statement is true by property of pseudo-random generator. So basically the seed is not known publicly or not known to the adversary. Seed is chosen uniformly randomly, and what by the security of PRG, what happens in the security game of PRG is, if you remember, that there will be a challenger and an adversary, and the challenger may generate output using either PRG, or it can generate a stream of output generated truly randomly. Okay, and it sends that string, let's say y is generated either by PRG or by truly random bits, and it sends y to the adversary. Just seeing the y, the adversary's job is to guess whether it is seeing an output from PRG or it is seeing an output from truly like it is seeing truly randomly generated bit string. Okay. So without the knowledge of seed only, because the PRG algorithm itself is public, seed is only the unknown information, and the adversary actually is for the adversary's view, the PRG string is in. So for the view of adversary, the PRG output and truly randomly generated output are indistinguishable from each other only if the seed is unknown to it. So first option is correct and second option is wrong. Adversary can query random oracle with any input of its choice. That is true actually. In case of PRG, the adversary cannot query as such. Like there is PRG is something that it starts with some seed and it continues to generate pseudo randomly generated bit string, right? There is no such query and response game between them, right? But in case of random oracle, actually the adversary is allowed to give some input X to the oracle and gets back response Y from the random oracle. And the property of random oracle ensures that if X has not been queried to the random oracle beforehand, then the output of the output Y corresponding to that input X looks or appears to be random and uniformly distributed over the output space to the adversary, okay, or to the user of random oracle in general. So third option is correct, and the output of random oracle on some query input appears to be independent uniformly random over the range if the query is made by an entity for the first time. So if X has been already queried to the random oracle by the user and it has seen the output Y corresponding to that, then if it again query with the same input, it is bound to see Y. Okay, that is fixed. But if it queries with some new X dash, then the output H of X dash will be independent of H of X and it will be uniformly distributed. So yes, both option is also correct. So only incorrect option is that seed of the PRG is known to adversary. Proceeding to the next problem. Which of the following are true for a commitment scheme? Security of commitment scheme relies on the collision resistance property of the underlying hash function. Hiding property of a commitment scheme handles the case when the receiver may be corrupt. Binding property of a commitment scheme handles the case when the sender may be corrupt. A commitment scheme built upon collision resistant hash function is secure assuming random oracle model. So let's discuss one after another. First option, security of commitment scheme relies on the collision resistance property of the underlying hash function. This is okay. This is true for the binding scheme only. Okay. However, it is necessary for the hash function to be collision resistance, because otherwise binding property of the commitment scheme will not be satisfied, as I already discussed. That if there has to be two such message and corresponding randomness such that message M1 randomness R1 and message M2 and randomness R2 map to the same commitment value C, then basically underlying hash function is not collision resistant. So provided the underlying hash function is collision resistance, an adversary cannot come up with adversary means here the corrupted sender cannot come up with such message randomness pair which maps to same commitment. Okay. So first option is correct, and okay, actually first option is not correct, because as I said that binding property of the commitment scheme relies on collision resistance property of the underlying hash function, but the another required property of commitment scheme is hiding property, which can be satisfied only assuming the random oracle model. Okay, so together in general we have to say that in order to prove security of a commitment scheme based on hash function or hash based commitment scheme, we have to go to random oracle model only assuming collision resistance of hash function is not enough. So first option is wrong. And the fourth option, if you see, a commitment scheme built upon collision resistant hash function is secure assuming random oracle model, that is true due to the same reason. So first and fourth option we have already seen. Let's move to second and third options. So it's given that hiding property of a commitment scheme handles the case when the sender may be corrupt. Okay, this is actually opposite. So hiding property of commitment scheme handles this case when the receiver may be corrupt. Why? Because if you remember, in the commit phase, the sender chooses some random R and it commits the message M such that message M and randomness R is mapped to some commitment C, and C is sent to the receiver. Now, the hiding property ensures that the receiver should not learn the underlying message M by seeing the commitment C. That is the hiding property. C hides M inside it. Okay. So this statement is wrong actually. Hiding property of commitment scheme handles the case when the receiver may be corrupt who tries to gain information about M by using C. So it should not be able to do that by hiding property of commitment scheme. And binding property of commitment scheme handles this case when the sender may be corrupt. Because what the sender can try to do is that first it takes some message M1 and randomness R1 and commits the value C to the receiver. Now, when the receiver asks for the opening information from the sender, it actually sends some other pair M2 R2 such that when the receiver computes commitment on its side on M2 and R2, it gets the same commitment value as C, but which is not expected the case. Whenever a commitment opens, it should always be the underlying message committed under the commitment C should never change. So such M1, M2 cannot be found. So yes, that's why binding property of commitment scheme handles this case when the sender may be corrupt. Second and third option are wrong. Okay. Proceeding to the next question. Which of the following is or are correct? Key derivation function can be built upon hash function modeled as random oracle. Okay. This statement is true. Okay. Because collision resistant function, collision resistant hash function has application in key derivation function, where two parties who has some pre-shared information which is highly unpredictable by some third party, and from that pre-shared information it actually try to generate some key, and the key should be actually uniformly randomly distributed over the key space. Okay. And for that you can use hash function, which is nicely described in the lecture also. So for that you need the hash function to be random, to be modeled as random oracle. Hiding property of commitment scheme can be proved by collision resistance of underlying hash function. I already discussed this thing, that binding property of commitment scheme can be proved by collision resistance of underlying hash function. To prove hiding property, you need to resort to random oracle model. Binding property of commitment scheme can be proved only in random oracle model. The third statement is again wrong. I already discussed it. So only correct option here is the first one. Proceeding to the next question. Choose the correct options from the following. If an encryption scheme is CCA secure, then it is also an authenticated encryption scheme. If an encryption scheme is an authenticated encryption scheme, then it is also CCA secure. If an encryption scheme is an authenticated encryption scheme, then it is also CPA secure. If an encryption scheme is CPA secure, then it is also an authenticated encryption scheme. So there are four kind of statements here. So let us remember what is authenticated encryption scheme. Basically, by authenticated encryption scheme, you want to achieve the three main target of cryptography in general, that is confidentiality, integrity, and authenticity. Okay, so confidentiality is achieved by the encryption scheme, underlying encryption scheme, and then you also achieve integrity and authenticity by ensuring another property called ciphertext integrity. So to given an encryption scheme, in order to ensure that that encryption scheme is actually authenticated encryption scheme, you need to satisfy two property. One is CCA security, another is ciphertext integrity. CCA security ensures confidentiality and ciphertext integrity ensures both integrity and authenticity. And by CCA security, you already know that the adversary actually is given access to encryption oracle and decryption oracle, and the adversary should achieve semantic security even, I mean, the encryption scheme should achieve semantic security even when the adversary has access to encryption and decryption oracle. In other words, the adversary should not be able to distinguish the encryption of M0 from an encryption of M1 when provided with access to both encryption oracle and decryption oracle. That is the definition of CCA security. And as we know that authenticated encryption scheme requires it to be CCA secure and to have ciphertext integrity. What ciphertext integrity says is that if you have like if the adversary has seen some valid ciphertexts, okay, corresponding to some messages, so as it already has access to encryption oracle, then it has already seen some message ciphertext pair. But even after that, it should not be able to come up with some valid ciphertext which decrypts to such message which is not seen by it previously. Okay, some new message basically. What in the query phase, whatever plaintext ciphertext pair it has seen, the new ciphertext that it comes up with, it should be a valid ciphertext and should decrypt to some another new message. Okay, what do I mean by valid ciphertext is that the adversary can pick up any random sample from the ciphertext space, but it can be the case that when decrypted, it actually gives out bot. Okay, bot is some symbol which denotes that the ciphertext is invalid. In case of authenticated encryption scheme, the decryption algorithm can return either some plain text or bot. Bot means that the ciphertext you provided to be decrypted is not a valid ciphertext. So ciphertext integrity ensures that the adversary is never able, the adversary is not able to come up with valid ciphertext which maps to or which decrypts to some unseen message. Okay. Except with negligible probability, of course. Now, if we, so I just repeated this thing in order to recall the concept of CCA security and the concept of authenticated encryption and concept of ciphertext security as a, sorry, ciphertext integrity. Now, looking at the options, if an encryption scheme is CCA secure, then it is also an authenticated encryption scheme. This is wrong because CCA security is necessary for an encryption scheme to be authenticated encryption, but that is not the only property. It also has to be satisfying the ciphertext integrity property, right? So first option is wrong. Second option, if an encryption scheme is an authenticated encryption scheme, then it is also CCA secure. This is true. Okay, I already said. Now, if an encryption scheme is an authenticated encryption scheme, then it is also CPA secure. Of course, a scheme, if it is CCA secure, then it must be CPA secure as well, right? Because CCA security is even stronger concept of security than CPA security. So if it is CCA secure, then it has to be CPA secure. And then if an encryption scheme is CPA secure, then it is also an authenticated encryption scheme. This is again wrong because for authentication encryption scheme, we need to satisfy CCA security as well as ciphertext integrity. So the only correct option here are second and third option. Proceeding to the next problem. So There exists a server A who wants to broadcast message to n recipients B1 to Bn in an authentic manner. We are not interested in privacy, but in integrity and authenticity, where each user should be assured that the messages it receives are indeed sent by it. For this, the users decide to use a MAC where server A shares a secret MAC key K with B1 to Bn, and each message from the server to the receivers is accompanied by a MAC tag computed with key K. Okay. Now you have been given some options that using a CMA secure map solves the problem. Using an SCMA secure map solves the problem. Neither a CMA secure map or an SCMA secure map can solve the problem. And using an information theoretically secure map solves the problem. So, if you would like to answer. Okay. So just to recap once, CMA secured map, what is chosen message attack? CMA is chosen message attack, and CMA secure map ensures that an adversary, even after seeing some message tag pair, valid message tag pair of messages chosen by itself, it should not be come up with some M star T star valid message tag pair such that M star was not among the query messages seen by it in the queries. And SCMA security ensures that it need not be the case that M star does not belong to any of the query phase messages. It can be, but overall M star T star, this pair should not be equal to any of the valid message tag pair already seen by the adversary. So that is the difference between CMA and SCMA security. Anyway, here in this question, it is actually very simple to notice that they have said that the server A shares the secret MAC key K with all the N recipients. So all the N recipients has access to the MAC key K. If that is the scenario, now like A can the server A can send some message M encrypted with some message M along with its tag computed with the key K to, let's say, BI. Now some other BJ also has access to this key K, so it can come up with valid message tag pair of some M dash comma T dash such that T dash is also computed with the same MAC key K. So this will be essentially a valid message tag pair, and it can be sent to BI. Okay, so it so any BI basically can generate and communicate with each other using the same key K. So if BI is a corrupted party, it can send anyone some valid message tag pair of its choice, which is not the scenario. Basically here, A only wants to broadcast message to all N recipients, and A is the only authorized one who should be sending valid messages to all of them. But here in this scenario, all the N clients, B1 to Bn, having access to the key K, can send message to each other, and those messages will be satisfying message integrity, right? Because they will have valid tag with them. So no one can distinguish whether it is seeing a message from some other BJ or from A, right? So it is neither CMA secure nor SCMA, like any MAC what you use, whether it is CMA secure or SCMA secure, does not matter because the key K is known to everyone. So also information theoretically secure MAC also cannot solve the problem. Okay, proceeding to the next problem. So let pi equal to Jane encryption and decryption, three algorithms are given, that is a symmetric key encryption scheme with message space and ciphertext space M, and C is L-bit binary string. Then consider a variant pi dash, Jane ENC dash and DEC dash with message space and ciphertext space M and C dash. So message space remains the same and the ciphertext space actually changes to C dash such that it is L plus 1 bit binary string. Now encryption ENC dash K M is defined as ENC K M concatenated with 0, and accordingly decryption so DEC dash K of C is defined as DEC K of C0 to L minus 1, that is it just uses first L bits of the ciphertext and call the original decryption algorithm with key K. Okay, now some options are given that if pi is multi-message COA secure, then pi dash is also multi-message COA secure. COA, if you remember, ciphertext only attack, where an adversary is observing the public communication channel and it can just see ciphertext communicated through that channel. So ciphertext only attack is the adversary is just able to see the ciphertext. It has no knowledge about the underlying plain text and it cannot gain any knowledge either by seeing the ciphertext, which is ensured by the COA security. And if it is multi-message COA security, basically in one single session through the public channel, there will be communication of multiple ciphertext at a time. So that's it. Now options are that this was the first option. Second option is if pi is CPA secure, then pi dash is also CPA secure. Third option is if pi is CCA secure, then pi dash is also CCA secure. And if pi is an authenticated encryption scheme, then pi dash is also an authenticated encryption scheme. So the security model is increased gradually from top to bottom. COA security is the most weaker definition, and then comes CPA security, where the adversary has more power. In CCA security, the adversary has even more power, having access to decryption oracle, and in authenticated encryption scheme, here not only we ensure CCA security, but we also ensure ciphertext integrity. So this is more stronger scenario. Now for analyzing that whether pi dash maintains the property of multi-message COA security from pi. So you see that what this encryption scheme, the modified encryption scheme ENC dash does is that it just repeats the ENCKM and then concatenate a 0 with it. So whenever an adversary in the modified pi dash sees a stream of ciphertext, okay, a stream of ciphertext, then the form of those ciphertext will be so C1 will be ENCK M1 concatenated with 0, C2 will be ENCK M2 concatenated with 0, and so on. So such multiple number of ciphertext is seen by the adversary, and the last 0 is not helping the adversary to gain any extra information about the underlying message M, because this finally boils down to the problem of multi-message COA security of the original scheme pi, because just ignoring the last 0, the adversary sees the corresponding multiple ciphertext corresponding to the original scheme pi basically. So it does not get any extra information about the underlying message M by seeing one extra 0 at the end of the original ciphertext, right? So basically the game remains exactly same. Okay, so multi-message COA security is directly depending upon the multi-message COA security of Pi. So if Pi is multi-message COA secure, then PyDAS is also multi-message COA secure. The second option, if Pi is CPA secure, then PyDAS is also CPA secure. This is also true according to the same logic. Even if the adversary gets access to the encryption oracle in our security game of PyDAS, then for each response it gets from the encryption oracle, this will be nothing but the response it would have got from the game in Pi and then concatenate 1,0 with that. So it again, the encryption oracle access does not give any extra information to the adversary, which it can use to distinguish encryption of M0 from encryption of M1. Looking at the third option, if Pi is CCA secure, then PyDAS is also CCA secure. Now comes the role of decryption oracle. If the adversary in the scheme PyDAS is allowed decryption oracle access in case of CCA security game, then actually you see that it can exploit that thing to distinguish between encryption of M0 and M1. How? So let's say that it has seen the challenge ciphertext. Okay, just let me proceed to the next slide. So here to go, let M0 and M1 be the plain text chosen by adversary in the challenge phase. Okay. So the challenge phase plain text are chosen by the adversary itself. Let's say they are M0, M1. Then challenger encrypts any one of them, say MB as CB equal to encryption K of M concatenated with 0. That is how ENC-K is defined, right, in our scheme of PyDAS. So that is the ciphertext CB corresponding to, it should be MB actually, okay, encryption K MB concatenated with 0. So either M0 or M1, depending on the bit B, which is randomly chosen from 0 or 1. Depending on MB, the ciphertext CB is generated in this way. Now, with the access of decryption oracle in the post-challenge query phase, that is, after seeing the challenge ciphertext CB in the post-challenge query phase, the adversary now query the decryption oracle with ciphertext C dash. And what is C dash? C dash is basically the first L bits of CB and then concatenated with 1. So you basically replace the last 0 of your challenge ciphertext CB with 1. So C dash is no longer equal to CB. You remember that in CCA security game, the adversary is not allowed to query the decryption oracle with the challenge ciphertext itself. Okay, so it cannot query the decryption oracle with CB itself, but it can query with C dash, because C dash is just flipping last bit of CB. Okay, now what happens? So the response of decryption oracle will be, so the way DEC-K is defined, decryption of the scheme PyDAS is defined in such a way that it is nothing but the original decryption operation with respect to the first L bits of the ciphertext. So first L bit of the ciphertext, if you notice, first L bit of C dash is exactly equal to the first L bits of CB. So in the decryption, actually only first L bits are used, and first L bits of CB and first L bits of C dash are exactly same. And now whatever is the decryption value or the underlying plaintext value of C dash is equal to the underlying plaintext value of CB. So with probability 1, the adversary can easily recover the underlying plaintext value of CB. Okay, so it can distinguish the encryption of M0 from encryption of M1 with probability 1. So this is not certainly CCA secure, and because it is not CCA secure, we already mentioned that in order to achieve authenticated encryption, we need to ensure both CCA security and ciphertext integrity. And because CCA security only fails here, then PyDAS is not authenticated encryption as well. Irrespective of whether Pi is authenticated encryption or not, PyDAS is not an authenticated encryption. So only correct option here are the first two options. Okay. So let me proceed to the next problem. Let M0, M1 be the plain text chosen by adversary in the challenge phase. Okay, sorry. Next problem. Let pi equal to gen enc dec be a symmetric key encryption scheme with message space m. We construct a new symmetric key encryption scheme pi dash, gen dash, enc dash, and dec dash for new message space m dash as follows. The key generation algorithm gen dash outputs k equal to k0, k1 as its key, where gen dash involves two independent instances of gen, which outputs k0 and k1 respectively. To encrypt a message m0, m1 belonging to m square, so the message space m dash is nothing but m square, where m is the message space of the original encryption scheme. Okay, so the output is consisting of two elements from the message space m, m0 and m1, and the encryption algorithm enc-k of m0, m1 outputs c0, c1 as the ciphertext, where c0 is equal to enc k0 of m0 and c1 is enc k1 of m1. Decryption algorithm is dec-k of c0, c1 outputs dec k0, c0 and dec k1, c1. So basically, what is happening? You have two messages from space m, and together you are encrypting m0, m1 using the original encryption scheme with respect to key k0 and k1 respectively. And then during decryption also, you decrypt these two ciphertext c0, c1 with respect to key k0 and k1 using the original decryption algorithm of scheme pi. Now there are some statements. If pi is multi-message COA secure, then pi dash is also multi-message COA secure. If pi is CPA secure, then pi dash is also CPA secure. Pi is CCA secure, then pi dash is also CCA secure. And if pi is an authenticated encryption scheme, then pi dash is also an authenticated encryption scheme. So here also, if you just notice the scenario, in case of multi-message ciphertext only attack scenario, uh, in case of our modified scheme pi dash, you see some sequence of ciphertext in the public channel in the form of C1, C2 to some CQ, where each of CI is actually containing two parts, CI1 and CI2, where CI1 is encryption of some message MI1 with respect to key K0, and CI2 is the ciphertext corresponding to message MI2 with respect to key K1. Okay. So basically, all these C1 to CQ is consisting of two ciphertext corresponding to the original encryption scheme pi, and some of them are with respect to key K0 and some of them are with respect to K1. Basically, half of them. So you can think of the sequence C1, C2 to CQ as Q number of encryptions with respect to encryption scheme pi and with respect to key K0. So half of the ciphertext, let's say, of the form CI1. So Q number of ciphertext CI1 are with respect to key K0 and the original scheme pi, and the adversary is also able to see Q number of ciphertext of the form CI2 with respect to original scheme pi and the key K1. So the COA security of the modified scheme pi dash boils down to the COA multi-message COA security of the original scheme pi, right? No other extra information is available to adversary by the modified encryption scheme. So we conclude that if pi is multi-message COA secure, then pi dash is also multi-message secure. And same applies for CPA security as well, because when the adversary has access to encryption oracle, it basically sees encryption with respect to scheme pi and with respect to two different keys K0 and K1. So at the end of query phase, the adversary actually has two set of uh, two set of message ciphertext, like two list of message ciphertext pair. One list is corresponding to key K0 and another list is corresponding to key K1. Otherwise, it is all same with the original encryption scheme pi. So if pi is CPA secure, then pi dash will also be CPA secure, because this information cannot be used to gain any extra information about how to distinguish encryption of M0 from encryption of M1. Okay. Now coming to CCA security, we will prove that even if pi is CCA secure, pi dash is not CCA secure. How? That I will show in the next slide actually. So here you can assume the scenario where adversary generates or chooses plaintext M0 M1 in the form that M0 is M comma M, M belongs to capital M, the message space. Okay. So M0 is of the form M comma M and M1 is of the form M comma M dash, where M is not equal to M dash. So these are two plaintexts chosen by the adversary in the challenge phase. And in response, the challenger encrypts any one of them, say MB. So the challenger chooses either M comma M or chooses M comma M dash, any one of them denoted as MB, and outputs corresponding ciphertext CB, where CB has again two parts, CB1 and CB2. Now, if the adversary is somehow able to determine if CB2 is an encryption of M or M dash, then it is done, right? So, because the way we have chosen these two plain text, one is M comma M and another is M comma M dash. So the last part of the ciphertext, that challenge ciphertext, that is CB2, second part of the challenge ciphertext, this can be encryption of either M or M dash, depending on whether MB is equal to M0 or MB is equal to M1. Okay, so the adversary is now required to determine whether CB2, the second part of the challenge ciphertext, is an encryption of M or encryption of M dash. So to determine that, what the adversary can do is that it makes use of the decryption oracle in the post-challenge query phase to query with the ciphertext C dash of the form C comma CB2. So just quite similar to the previous example here, in the post-challenge query phase, the adversary is querying the decryption oracle with some new ciphertext. Of course, C dash is not equal to the challenge ciphertext CB, but the second part is exactly equal to the second part of challenge ciphertext. So the second part is CB2, for which we need to know the underlying plain text, whether it is M or M dash, and C can be any valid ciphertext seen by the adversary in the query phase. Okay, query phase to encryption oracle. So C can be any valid ciphertext. Okay, so it has access to encryption oracle, so it can see valid ciphertext corresponding to any plain text basically. So first half of any or any half of any valid ciphertext can be used as C, but the second part need to be of same as the second part of the challenge ciphertext, that is CB2. Now when it queries C dash, queries the decryption oracle with this query ciphertext C dash, then it gains information whether like it gains the decryption of C and CB2. And as CB2 is decrypted, if it is M, then the adversary concludes that the challenge ciphertext was encryption of M0. And if the decryption corresponding to CB2 is M dash, then the adversary concludes that the challenge ciphertext is corresponding to the underlying plain text M1. Okay, so with probability 1, basically now the adversary can distinguish encryption of M0 from encryption of M1, hence it is not CCA secure. So pi dash is not CCA secure, and as it is not CCA secure, it is of course not a authenticated encryption scheme. Okay, proceeding to the next question. So let ENC DEC be a secure cipher. Consider the following derived ciphers. So you have been provided with two encryption scheme, basically proposed encryption scheme. First one is your question is that you have to show the first scheme is not AE secure. So first scheme is not an authenticated encryption scheme, but second scheme is authenticated encryption scheme. So let's follow them one after another. First one is ENC-K of M is equal to ENC-K of M and ENC-K of M. You are generating two ciphertext corresponding to the same message M using the original encryption algorithm ENC. Notice that as encryption algorithm is randomized, so even though you write ENC-K of M, ENC-K of M 2 times, they may not generate the exact same ciphertext corresponding to them. So it can be some C1, it can be some C2, both corresponding to the underlying message M. So that is how encryption is defined here. And DEC-K of some C1, C2 is defined as you first check whether, so you decrypt both C1 and C2 with respect to key K and check if both gives back the same underlying plaintext. If that is the case, then you return the corresponding plaintext. Otherwise, you reject. So if C1 and C2 are not encryption of same message, then you reject the sample because it is not a valid ciphertext. According to the definition of encryption algorithm, both the parts should encrypt same underlying plaintext. If that is not the case during decryption, then you conclude that the C1, C2 is not valid ciphertext and you reject, okay, or you return bot. Now, analyzing this scheme actually, so let me proceed to the next slide. So first scheme is not actually CCA secure, and then we conclude that it is not AEA secure also, because CCA security is necessary property for achieving AE security. AE means authenticated encryption. So how do you do that? So let M0 and M1 be two plaintext chosen by adversary in the challenge phase, and the challenge ciphertext encrypts any one of them and returns CB corresponding to MB, which depending on value of the B, either 0 or 1. So challenge ciphertext CB has the form CB1, CB2. Now the adversary may query the decryption oracle with a ciphertext C dash, which has form C, CB2. Again, we are providing the second part of the ciphertext as exactly equal to the second part of the challenge ciphertext, but it is not essentially, it is not equal to CB basically, because the first part C is not equal to CB1, because otherwise exactly CB cannot be queried to the decryption oracle, as we already mentioned. Now, what is C? C has to be a valid encryption of M0 obtained from encryption oracle query. Okay. So, if you query the encryption oracle with plaintext M0, what you get back in the form of C1, C2, so that both C1 and C2 are valid encryption of M0, right? So you can use any one of those encryption, either C1 or C2, as C here. Okay. Then what happens? You are providing to decryption oracles such a ciphertext where the first part you know to be encryption of M0, but the second part you don't know whether it is encryption of M0 or M1. Now the decryption function is working in such a way that it returns bot whenever decryption of C is not equal to decryption of CB2. So you already know that decryption of C will be M0. That is how you chose C to be. Okay. So decryption of C is guaranteed to give or return M0, but decryption of CB2, if it is equal, so it will be either M0 or M1. So if it is M0, then the decryption will return plaintext M0 certainly, and the adversary now knows that CB is actually encryption of M0. And if it returns bot, that is decryption of C is M0 and decryption of CB2 is M1, that was the mismatch occurs and the decryption oracle returns bot. If that is the case, then immediately adversary knows that the challenge ciphertext CB actually encryption of M1. So that's how with probability 1, the adversary is able to differentiate between encryption of M0 and encryption of M1 in this case. Hence, this scheme is not CCA secured, and which implies that it is not authenticated encryption as well. And then in the second proposed construction, so ENC double dash KM is defined in a way that first you get some encryption C corresponding to plaintext message M and key K, ENC K of M, you compute C and then output C comma C. So it is a bit different from the first scheme. In the first scheme, encryption algorithm being a randomized algorithm, the first part and second part may not be the same, but here you run ENC K of M only once and then you output C comma C. Okay. And in the decryption algorithm, you first check whether C1 is exactly equal to C2. It's not the case, like in contrast to the first scheme where you decrypt both C1 and C2 with respect to K and then check whether the underlying plaintext are same or not. Here actually you are checking whether the ciphertext themselves are exactly equal or not. If C1 is equal to C2, then you will decrypt C1 with respect to K and return the underlying plaintext. Otherwise, you reject ciphertext or you return bot. Now, you notice that this scheme is, although it is having two parts in the ciphertext, it is not different from the original scheme ENC-DAC. Okay, why? Because you are just returning C comma C, right? So it is no different than returning just C to the adversary. Okay, the adversary is whenever it queries to the encryption oracle, it always say C the same first half and second half C comma C in the ciphertext, and whenever it queries to the decryption oracle, even if it changes the decryption oracle, sorry, the decryption query to some C comma C dash by changing the second half of the challenge ciphertext, let's say, then it gets cancelled immediately by the decryption oracle because C is not equal to C dash. So only valid query to decryption oracle is of the form C comma C. Now, if C is not a valid ciphertext with respect to scheme pi, then that is handled by the original scheme. If let's say the adversary is querying the decryption oracle with some C dash comma C dash. Now, if C dash is not a valid ciphertext with respect to the original scheme, then that is handled by the AE security of original scheme itself. So if the original scheme is AE secure, then this derived scheme ENC double test, DEC double test is also AE secure because by the use of encryption oracle or by the use of decryption oracle, the adversary gains no extra information than the original ENC-DAC scheme. Okay. So we conclude that the second scheme is AE secure. So that is all for today's session. Thank you and thanks for joining.